Hello, my dear students. I am B S Pandey, your physics lecturer. The students, we have studied in lecture number 66 about the eddy current. Okay, my dear students. Today we will study the application of eddy current. Today we are in lecture number. Actually, I was in 67. We were in lecture number 67. It is lecture number 68. And NCERT chapter number 6, it is Electromagnetic Induction. And today we will see the application of eddy current. The few application I have mentioned, my dear students, but today we will see that application with the help of a video clip that I have got from internet. Okay, I'll give the reference of that video also if you want to see the full lecture or the full video over there. But that video will give you the experimental and the animation that enable you to understand the applications of eddy current. So let us see that video clip.
I would like to do another demonstration of eddy currents and the resulting magnetic braking that will occur on a pendulum. So what I have here are two magnets. Okay, so this is like the north pole here of this magnet and the south pole here of this magnet. So there's a fairly uniform field in between here, and these are actually fairly strong magnets. So if I actually put a piece of steel in here, if this were a piece of steel, it would stick and I probably wouldn't be strong enough to pull it apart. But what I have here is a piece of aluminum. Okay, so aluminum is paramagnetic, so it is only weakly magnetized, so it's not really attracted to the magnets. Okay, so I also have two other pendulums. Okay, this one has slots in it, and this one, the slots go all the way to the bottom, so there's no connection along the bottom. Okay, and any of these I put in here will freely swing. Okay, so now let's see what happens when I try to swing this one through the magnetic field. Okay, notice how it breaks and stops. Now if I did the one with the slots, we see it also breaks and stops. Not quite as quickly. And finally, the ones with the grooves so that there's no connection on the bottom swings freely. Okay, what is happening is that as this one is swinging into the field, you have a changing magnetic field in this region. So that sets up a resulting current such that the magnetic field generated by the current opposes the increase in magnetic field. So that will be a field in the opposite direction, and that is what's causing the braking. Whereas in this one, where we have these grooves, you can't get the circulating eddy currents because of the disconnection between these regions of the metal, and that's why you don't set up those strong induced magnetic field currents and resulting magnetic fields. Let's see if I can further clarify the eddy currents that will start to occur and the resulting magnetic field due to those eddy currents. So let's say we're sitting in that gap between those two magnetic poles, and we're looking, say, from the north to the south pole. So this circle signifies the area of one of the poles, and these X's signify that the magnetic flux density is into the page. Okay, so the aluminum pendulum now is trying to slide in like this. Okay, so as the aluminum pendulum is going in, what we see is that in this area we have an increasing magnetic field inside the aluminum into the page. So that we know is going to induce a current, so that that induced current generates a magnetic field that opposes the increasing field into our aluminum here. So that will be a counterclockwise circulating currents are going to start to set up here. So that's going to generate a magnetic field that's coming out of the page and opposing the increasing field into the page due to the aluminum sliding into the field. Now when the pendulum with the slots slides into the magnetic field area, these eddy currents cannot flow because now you have discontinuities, you have the high resistance air gaps, so you're not going to get those eddy currents and the resulting same large opposing magnetic field. So the kinetic energy of this pendulum as it's sliding in is converted to heat in the aluminum due to the eddy currents.
So my dear students, I hope you got the great idea about the applications of eddy current. Alright, now we'll start today the another topic. It is inductor and inductance. Okay, so let me start the next topic. It is induction or inductance. My dear students, to understand this induction or inductance, let we understand first the inductor. Actually, this inductor is a device. It is an electronic device. And this device works same as the capacitor works. Actually, the capacitor works to store the energy, and which type of energy? It is the electrical energy in presence of electric field, and this inductor used to store the energy in presence of magnetic field. That is the magnetic energy in presence of magnetic field. Okay, there will be a few questions on the basis of board also, but we are going to study here about the inductor. You will see this inductor having a shape. The symbol of the inductor will use this one. It is represented by L. Alright, this is L. My dear students, actually this inductor, it is made as the solenoid. You can think. We have studied over a non-conducting hollow cylinder. We winded a insulated conducting wire and the solenoid were formed. In same way, this inductor, actually this is of a spring like, okay, and this is a inductor. My dear students, before starting the other thing about this topic, let me see a video clip.
Is a coil of wire wrapped around a magnetic material. Current flowing through the inductor creates a magnetic field, and magnetic fields do not like to change. As a result, an inductor is a device which tries to prevent the current flowing through it from changing. If the amount of current flowing through the inductor is constant, the inductor will be happy and it will not generate any forces on the charged particles flowing through it. In this case, the inductor behaves just like a normal wire. On the other hand, if we try to interrupt the current flowing through the inductor will generate a force, trying to keep the current flowing through it. If an inductor is connected to itself, and there is no resistance in the circuit, the current will theoretically continue circulating forever. However, unless we are using superconductors, all wires have some resistance to them, and the current will eventually decay to zero. The larger the resistance, the faster the current will decay. But the larger the inductance of the inductor, the slower the current will decay. Once the current is at zero, the inductor will want to keep the current at zero, due to the fact that an inductor tries to prevent the current flowing through it from changing. Therefore, when we connect this inductor to a circuit, the inductor will initially create a force trying to prevent the current through it from increasing. But the current will slowly increase. The larger the inductance of the inductor, the slower the increase in current will be. After the current has stopped increasing and has reached a steady value, the inductor will then again be happy and not generate any forces. But when we try to turn off the current flowing through the inductor will then generate a force to try to keep the current flowing through it at this new constant value. If the inductor is then connected to a resistor, the voltage across the resistor will be the current multiplied by the resistor's resistance. The inductor prevents the current flowing through it from changing instantaneously. Therefore, the current flowing through the inductor immediately after we flip the switch will be exactly equal to what the current was before we flipped the switch, regardless of what the value of the resistor is. If the value of the resistor is extremely large, then the current multiplied by the resistance will also be extremely large. As a result, inductors can generate extremely high voltages, at least for a brief period of time. Since the current through an inductor cannot change instantaneously, when we try to disconnect an inductor from a circuit, we always need to provide a path for the inductor's current to flow. If we do not provide a path, the inductor's current will find its own path, such as through the air, through the open switch, or through other components that are not supposed to be conducting electricity. This can create very large voltages and cause considerable damage to the circuit. The ability of an inductor to create large voltages makes them very useful in the design of power supplies. But this ability also means that care must be taken to ensure that we never try to switch off an inductor without providing a path for its current to flow in.
So, my dear students, with the help of that previous clip, you must have understand about the inductor and the inductance and how this inductor work, or might be the little concept of inductor. Let me start with the beginning about this inductor and the energy which is stored by inductor. Actually, this is the inductor, my dear student. As I told you, this is the symbol of inductor. As you apply here the source of current, that is the voltage, what happens as soon as you switch on this battery, current start flowing, and this current start moving through this inductor. As the current established through this inductor, remember this inductor start producing magnetic field. As the magnetic field is produced, suppose here the magnetic field, as we know that the solenoid also form magnetic field inside. Suppose this is the pattern of magnetic field. I'm drawing here the magnetic field lines. Okay. Now what will happen? Think carefully. What will happen if the current is, suppose this is the current, and if this current is constant, what will happen? The magnetic field, it will be the constant. But as soon as this current will change, the magnetic field will change. Now this inductor, if this is the inductor, this is the inductor, as the magnetic field are linked, magnetic field lines are linked with this inductor, as soon as the current will change, what will happen? The magnetic flux will also change. And we know that due to change in magnetic flux through any coil, that induces an EMF. The first thing. And second thing, which are very important, that according to Lenz's law, the induced EMF will oppose the cause. And why this EMF induced? Due to change in current. If the current is increasing in this direction, be careful. If the current is increasing in this direction, then a force will come in action to oppose this change in current. Actually, that particular word, it has been used in clip as the force. Okay. Here we will study that force with the help of that EMF, that is the electromotive force. Okay. As the current will increasing in this direction to change the magnetic field, that the flux will change. So there will be an EMF to oppose this change in current. If the current is increasing, so there will be the EMF induced in such a way that it will oppose the change in current, that is increasing current, and the EMF will induce in this direction, and that EMF is termed as, this EMF, it is termed as the back EMF. But remember, this will induced EMF, but back EMF. We got, this will be the direction if the current is increasing in this direction. If the current is increasing in this direction. Okay. Now, suppose you are having inductor in such a way the current is decreasing. This is the inductor. Okay. In this direction, this I is decreasing. Then what will happen? Here the current is decreasing. It means the current is moving in this direction to produce the flux. Here the flux linked with the coil, and this flux will induce an EMF to oppose the current. If the current is moving in this direction, that is the current decreasing, then the EMF will not accept this decrease in current to induce an EMF by changing flux. So the EMF will induce in this direction. If the current is decreasing in this direction, then EMF will induce in this direction to oppose. So here the EMF will induce in this direction, and here the back EMF will be in this direction. My dear students, in next chapter we will study the circuits, that is in AC, the circuits in which you will use the EMF across these inductors. In this chapter we will derive what should be the formula for the induced EMF, but this is the simple concept of inductor, my dear students. Remember one thing more. Suppose if the current is increasing in any inductive circuit, okay, in any inductive circuit, if the current is increasing, but after some time the current get established and it becomes steady, that is the current is constant. In that case the current is not changing, so there will be no change in flux, and in that case, if the total energy is stored by the inductor and the current is not changing, in that case this inductor behaves as an ordinary conductor. Remember, and we will study the resistance as we study the resistance of other conductor. Alright, all conductors, that is the inductors, have the resistance as well. My dear students, this property actually of inductor is a device, and this property by which it opposes the change in increase or decrease in current, it is called basically the inductance. Okay, it is called the inductance. Now we have some SI unit also for this inductance. Actually that property is called the induction, and the inductance, it's a mathematical form, and that the Henry will be the SI unit. Okay, so let's discuss here few more things. Now we are going to study here the coefficient of induction. Suppose here we are having a coil, that is the inductor coil, and the current is increasing. One thing which is very important that we discuss, my dear students, in a steady state that inductor will be behaves as ordinary conductor. Bear in your mind. See the current I, it is increasing. Of course there will be an back EMF in this direction. We'll try to find out the formula for this back EMF as well, and this is the flux linked with the inductor. We know that here the flux is changing due to the current. If the current will increase, the flux will increase. Current will decrease, the flux will decrease. It means the flux linked with this particular coil, it is directly proportional to the change in current. So here you can write the magnetic flux is directly proportional to the current. Am I right? Yes. And this is the magnetic flux, my dear students. As you'll find here the constant or proportionality, it is termed as L, and this is L is constant, which is called coefficient of inductance. Remember, here the EMF induced in the same coil in which the current is changing and the flux is changing. That's why this particular phenomena is also called the self-inductance. Okay, this is also called the self-induction or inductance. All right, and this coefficient of, you can say this is the coefficient of self induction or inductance. Okay, now if you wish to find the value of this L, then you can write L is equals to phi over I. It means to find the coefficient of that inductor, that is the coefficient of self-inductance, you need flux linked with the coil and the current, what the current is changing and it is moving. So you can find out the coefficient of self-inductance. My dear students, here you can find out the EMF induced also. I hope that you are able to see from this equation the EMF induced, that is the back EMF. According to Faraday, we know that, okay, you can write the heading, my dear students, the EMF induced in an inductor. According to Faraday, we know that the induced EMF, it is nothing but the minus d phi over dt. Am I right? Yes. So E induced, my dear students, we can write minus d and phi, it is nothing but the Li over dt. And this L is constant, so induced EMF can be written as L di by dt. Remember, EMF will not induce, there must be some flux due to the current, but EMF will not induce until current changes. If this current will be constant, I is constant, you can see this derivative will be 0 and the entire induced EMF will be 0. Here, I'm sorry, I left with this negative sign. And this negative sign representing this induced EMF will be opposite to the change in current. If this di by dt it is decreasing, then it will oppose. If it is increasing, then again it will oppose. And this negative sign actually explains that thing. Okay, my dear students. So this is L di by dt, the rate change of current times the self-inductance gives you the induced EMF across an inductor. Now, one thing, my dear students, we can study from here. Let me discuss a very simple experiment for this self-inductance. If you will be asked to write the definition of self-inductance, what you will write, my dear students? You will write actually the EMF induced in a coil due to change in flux or current in the same coil, and this phenomena is known as self-inductance or induction. Okay, now look at here. One experiment which is a very, very important, actually the eddy current application we have done. Alright, experiment. This experiment, actually I'm just quoting here, this is the question of your CBSE. This is an inductor connected with a bulb. In video, you have noticed how this glow of bulb increases and decreases, which is connected with the inductor. And here a resistance and another bulb. Both the bulb having the same resistance, same power, B1, B2, inductor and the resistance. In steady state, both the coil, that is the resistor and inductor, will have the same resistance. Here I am connecting a battery with a key. This is key. Okay, now the question, my dear students, what you will notice if the key is closed, and what you will notice in the glow of this two bulb as the key will off, that is open. Okay, so in both the case we have to study one by one. So the first case, one, when key is closed. Okay, in this case when key will close, what will happen, my dear students? As the key will close, the current starts flowing through both the resistor and inductor. It means current establishing and the current is increasing. As the current is increasing, of course, there must be some EMF in the bulb. Now, this EMF, once established, what will happen? The EMF once established and the current becomes steady, this bulb will glow with its actual power, as this bulb B2 is glowing. Remember, both having the same resistance will draw the same current. As soon as the switch will close, the bulb will glow, but bulb B2 is not glowing with its actual power. This B1 and the B2 as soon as this key will close, the B1 will have the dim light and the bulb B2 will glow. Okay? But why it happens? Actually, as the current is increasing, there will be the back EMF and an opposing force which will not allow the current to move easily through the bulb, and this bulb glow very small with very small rate. That is, it will be dimmed, and this is getting the current with its constant power and the value, so it will glow up. Now, case 2. When key is open. Now, after closing, the key is open. Remember, after closing, when the key is open, could you guess what will happen, my dear students? Now, we are having the two bulbs. Again, B1 and B2. As soon as the key will open, the current will be vanished through the resistor, so the bulb B2 will goes off. Now, through the bulb B1, as the current will move in this direction for a very short interval, for moment, the back EMF will be supporting in this direction and bulb will glow for a moment. This bulb will glow with its maximum power, and after that both will goes off. So this is a simple experiment, my dear students. I was thinking to explain before you. I hope that you can also understand this particular experiment. There are number of things you can discuss